Okay, mixtures of gases. A lot of gas samples are mixtures. They're not just a single gas, there's a bunch of different gases. Air is an example of a mixture of gases. So in air, 78% of the volume is occupied by nitrogen gas, 21% by oxygen, 0.9% by argon, 0.04% by carbon dioxide, and then there's other gases, but those are going to be even smaller percentages. These are not exact numbers, and they can vary a little bit, but to those sig figs, I think they're pretty accurate. So we talk about dry air versus like regular air, or we might call it wet air, just to emphasize. What makes something wet? It has water in it, right? So air can have water vapor in it. And we call that humidity, right? There's molecules of water floating around in the room. Because it's, what is it? 52% humidity in here. Only 31% outside. So we've got the nitrogen, oxygen, argon, carbon dioxide, and we also have water vapor in there. And knowing how much water vapor is in there is much trickier because humidity changes. Why is it more humid in here? Because we're in here perspiring and breathing. Yeah. Yep. That's a good question. Thank goodness this isn't a locker room where people were showering, because then it's like really, really humid. So sometimes we can think of a gas mixture as just being a single gas. We can measure its pressure, volume, and temperature in the same way, but then when we calculate the moles, we're going to get the moles of all the gases added together. The gases, even if they're mixed up, are going to behave independently of each other. So being mixed with other gases does not affect their behavior. So each gas is exerting a pressure on the container, and since that gas is not the only gas in the container, it's not the only one exerting the pressure, the single gas is exerting a partial pressure, part of the pressure that the entire mixture is exerting. So we can calculate the pressure due to a single gas in a mixture from the ideal gas law. So PV equals nRT. And if we want to know the pressure, we're going to divide by volume. And the pressure of the gas is equal to the number of moles of that gas times R times the temperature divided by the volume. And we could call this P sub N. That's the partial pressure of the gas N. So Dalton, the same guy of the atomic theory, also has a law of partial pressures. And what this says is when you have mixtures of a gas, if you add their partial pressures, they will equal the total pressure. And this is similar to how mass behaves. If you have a box of fruit, right, and you put in 3 bananas and 4 apples, and you know the mass of the apples and the mass of the bananas, the mass of fruit in the box is just the sum of them, right? So the same here, but we're talking about pressure. Oxygen toxicity occurs when your oxygen partial pressures are above 1.4 atmospheres. You don't need to remember these numbers. Hypoxia, hypo means below, so that's not enough oxygen. Oxygen starvation, that's when your oxygen pressures get too low. And so this is just a little chart showing you this green area is pretty healthy. The yellow's where you're getting in trouble, and the red is really bad. So breathing compressed air gives you a higher partial pressure of oxygen, but also a higher partial pressure of nitrogen, because the total pressure is higher. So if you're breathing nitrogen at a pressure above about 4 atmospheres, you end up getting a lot of nitrogen in your blood, and that leads to something called nitrogen narcosis, or also known as rapture of the deep, and it has symptoms similar to alcohol intoxication. So you can get drunk on nitrogen down at the bottom of the ocean. You don't want to be drunk down at the bottom of the ocean. You want to have a clear head, right? And not do something stupid like decide to pull off your mask or something. So up at the surface, we have total pressure of 1 atmosphere. So then the nitrogen is 0.78, oxygen is 0.21. Down here at 30 meters, we need a total pressure of 4 atmospheres. Now we've got 3.12 atmospheres of nitrogen and 0.84 of oxygen. So now we're getting to the situation where we're going to get too much nitrogen. So to avoid this, deep sea divers will breathe a mixture of gases other than air. And one of them is called heliox, which is helium and oxygen. So there's no nitrogen in it, so you can't get narcosis, nitrogen narcosis, right? I always, you can't talk when you're underwater, but everybody would sound like chipmunks. It would be really fun. So a diver breathes a heliox mixture with an oxygen mole fraction of 0.05. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So here we have oxygen mole fraction and partial pressure of oxygen. And they're asking us to find the total pressure. Well, we can think about this. The total pressure is going to equal the pressure of oxygen plus the pressure of helium. This mole fraction, though, that's this funny X, it's a Greek letter chi. We're given that the mole fraction of oxygen is 0.050. That's a fraction, like a percentage, so it doesn't have any units. So this makes me think of the equation that says the partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. If 50% of the gas is one thing, then 50% of the pressure is that thing. So I want to know the total pressure here. So I can divide both sides by the partial pressure. I think I can. The total pressure is going to equal the partial pressure divided by the mole fraction. So partial pressure is 0.21 atmospheres, mole fraction is 0.050. So to have a good amount of oxygen, 0.21 atmospheres of oxygen is the normal oxygen concentration at sea level. So breathing this gas, it would have to be at a pressure of 4.2 atmospheres. So what they do is, as they increase the pressure, they can change the mix of the gas. Any questions? Collecting gases. So, if you do an experiment and it generates gas, how do you catch the gas? And especially, how do you catch the gas without getting a bunch of air in there as well? So this is called collecting over water. So here we have our chemical reaction occurring. Zinc and hydrochloric acid is making hydrogen gas. We're doing this in a test tube connected to a glass tube that goes out and down and under and comes up in this inverted beaker. So to start with, this beaker was full of water. And this dish is full of water. And it kind of looks like the mercury mercury barometer. But because it's not 32 feet tall, none of the water comes out. So it would just stay at the top. But as hydrogen is created here, it increases the pressure, and so it's going to try to get out. And so it's going to come through here, and it's going to come up and bubble through the water and get trapped inside this beaker. As hydrogen gets in here, it's going to displace the liquid water. The water level will go down. But we're not going to have just hydrogen, because water evaporates. And so water will be evaporating from the surface into this space, and so we're going to end up with a mixture of hydrogen gas that we want and the water vapor that we didn't really want. But that's one of the simplest ways to collect a gas. The partial pressure of water is also called the vapor pressure of water, and as it turns out, that only depends on the temperature of the water. So that's really nice. Other people have done studies and measured the partial pressure of oxygen at these different temperatures. And they've done a lot of temperatures in between as well. Your book's just giving you a more simple chart here. So if we know the temperature, and if we're dealing with a gas and we're going to try to calculate the moles of it, we need the temperature anyway, right? We can look up the temperature of our gas and find out what the partial pressure of oxygen is, and then we can subtract it from the total so we can have the pressure of the gas that we're interested in. There are several questions like this on the worksheet. Collected over water, and it's not going to give you the vapor pressure of water. You have to go look it up. If it was on an exam, I'd give you a table or I'd give it to you in the problem. But on a worksheet, you can go look stuff up. So a sample of acetylene is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? So we've got this total pressure, we've got a volume, we've got a temperature, a vapor pressure of water, and the question is how many grams of acetylene? So we're trying to get grams of C2H2, and they just gave us all this gas information. What can we calculate from the ideal gas law? Moles of gas, right? So we can calculate moles of C2H2. That's from the ideal gas law. Can we convert that to grams? Grams to moles? Molar mass, right? So we're going to use the ideal gas law to calculate the moles of acetylene. But acetylene is not the only gas. So the total pressure is 738 torr. And the partial pressure or vapor pressure of water is 21 torr. So if we want the partial pressure of the acetylene, we're just going to subtract. (717) torr. Got a volume. Whoops. And a temperature. So the moles of gas is equal to pressure times volume divided by R times the temperature. So we want the pressure of the acetylene because we want the moles of just the acetylene. So here's, we end up doing this all the time. In fact, what some students do is they're like, well, 717 over 760, and that'll be in atmospheres. And then our volume, 523 times 10 to the minus 3 liters, 0.08206 liter atmospheres per mole Kelvin. And the temperature in Kelvin. They're not just being obnoxious by giving you these quantities in units other than atmospheres, liters, and Kelvin. Because when you measure the temperature, the thermometer gives you an answer in Celsius. If you're dealing with a small quantity of gas, you're going to measure it in milliliters, not in liters. And most barometers do not give you atmospheres. They're either going to give you torr, millimeters of mercury, or something stupid for science like inches of mercury. So 717 over 760, that's 0.943 if you're interested. So this is 0.020313 moles. Need to calculate the molar mass of acetylene. So I want the answer in grams, so I'm going to multiply by grams and divide by moles. See how the units cancel out. If I multiply by moles and divide by grams, I get some crazy quantity of moles squared per gram. Not very useful. So watch your units. So it's that many grams for 1 mole, 26.036. So 0.020313 divided by 26.036. So that's not very much, is it? Well, you've got a relatively small thing here. That's a half a liter, right? And the gas doesn't weigh very much because it takes up a lot of space. And so if you condensed it all down, it wouldn't weigh very much. So if we want to put this in scientific notation, 1, 2, 3, 4, this would be 7.80 times 10 to the minus 4 grams. Most of your calculators have a way that you can switch between decimal notation and scientific notation. It'll do that conversion for you. And I highly recommend doing that because I've seen a lot of people do this backwards and give me a positive exponent. This is a small number. I have negative feelings about small paychecks, right? I have positive feelings about big paychecks. No, I didn't have the answer there. Any questions?